The chi-square test allows us to see if there's an association between two categorical or binary variables. We put the data into a table. We might have some sort of exposure. Do you smoke? Yes or no? And then we might have some sort of outcome. But did you die? Yes or no? And what we're going to do is calculate a statistic that summarizes the data in this table. And in a very simple sense, the chi-square statistic is what would I expect to see if the null hypothesis were true, if nothing were going on? And then what did I actually observe? What did I actually get? And if you think about it for a second, the bigger a difference of what you would expect versus what you got might be a hint that something's going on. And so the chi-square statistic is going to be the sort of quantification of how weird is this freaking table if nothing is actually going on. So the way that this works, it's a little harder by eye to see what would I expect in a given cell. We saw in the last set of slides, we said 10 and 90, 10 and 90. If men and women were the same here, what would you expect to see for these numbers? But we have to calculate what is the expected cell count, and then we need to see what the observed is. The expected cell count, we look at this number right here. What do we expect to see there? If men and women are the same, and stats liking this is, again, not that many people like stats relatively, what would you expect to see for 58? The way that you can get that is this number here, which is called the column total, multiplied by this number here, which is called the row total, divided by this number here, which is called the grand total. 89 times 463, column total, row total, divided by the grand total. And that's going to yield what we say is the expected count for this cell. I'm going to show you one thing here. I just want to stress that this is a 2x2 table. And these are the 4 cells that we're thinking about. But by looking at the row and column totals, we can calculate the expected amount in each cell. So chi-square, the expected counts, we calculate. And then the observed counts, we count what you actually saw. And then we see how is what we actually saw relative to what we would predict. This is the same thing we've done again and again and again. Statistics is backward. What's the probability of seeing our data if the null hypothesis were true? Well, we know that. We've seen it again and again. It's called the p-value. That's what it is. So for each cell, like we saw, you calculate the expected count. The total of that row times the total of that column divided by the grand total. And so for each individual cell, you will get an expected. I'll just make up a number. Let's say in this cell, you get an expected count of 10 and a half. Then for that cell, you calculate what you actually saw, the observed. Students often get confused the difference between expected and observed. I'm not sure where that stems from, but observed is just what I got. I would expect to see 10 and a half people in this cell. And again, that number comes from whatever other numbers are in here. And how many people did I actually see in that cell? People who smoked and died, for example. Okay, let's say that it's 14. Now, the way chi-square works, and you can do this by hand, it's pretty easy to do, is take what you observed, 14, and subtract what you expected, 10 and a half, right? There's something going on here, a little suggestion that something's a little bit weird. Then you square these up. That's why it's chi-square. And then you divide by expected, which for this cell would be 10.5. We're going to walk through a longer example of this in the next set of slides. But what we see here is that each cell gets a little bit of a number, and then you add these up for each cell. This is the Greek letter sigma. Sigma is just sort of like S. It's like sum. You sum up every cell. This will calculate a number, which is the chi-square statistic. Then you have to think about, well, is that number weird or not? Is that number weird or not? Think for a second. If there were actually nothing going on, if the null hypothesis were true, and men 1090, women 1090, and that's actually what you got, how far are the observed from the expected? Well, I expected 10 and 90, and I got 10 and 90, and I expected 10. And every one of these would be 0. And when I add up 0, 0, 0, 0, 0, my chi-square would be 0. So if nothing's going on, you're going to get a chi-square somewhere around 0. But as these things start to differ, let's say 70 and 30, women love stats. Men, not so much. What would be the chance of getting this if men and women were the same? Well, it's kind of weird. We would see something like a big signal coming out of that. So we calculate your chi-square statistic, and then we have to plot it on some what would happen if the null were true. And clearly, if the null were true, it would be 0. You'd expect to get a little bouncing around randomly. You get some kind of signal, and then you turn that into a p-value. Here's the distribution of chi-square when you have different sample sizes. So there are an infinite number of chi-square distributions based on how many cells you have in your data. If you have a 2x2 table, the simplest kind, we talk about these distributions. We've seen this before. We talk about them with this word degrees of freedom. And degrees of freedom here is calculated with the number of rows minus 1 times the number of columns minus 1. So 2 minus 1, 2 minus 1, 1, 1, 1. So this green curve there is what you see you would expect to get if the null were true in a 2x2 table. As your tables get bigger and you have bigger and bigger things, because we're adding up each cell, we'll get bigger and bigger numbers just by chance alone. But we want to focus on that green curve. Take a look at this curve. This is what you would expect to see if the null were true. And then we think about what's our alpha level? What is the level at which we might declare statistical significance and say, well, that's weird. I wouldn't expect to get that. Maybe I'm really lucky, or maybe the null is not true. So let's say that our alpha level is 0.05. So take a look at that green curve there. What value corresponds to the area underneath that curve? That would be 5%. What chi-square statistic are we looking for that's going to be about 5%? And the number for that is 3.84. I didn't memorize that, but I've done this enough that I know. So if I zoom in on that curve right here, this number, 3.85, I get 5% of the curve over here. That just make I might have just made a small error. The number is 3.84. This number is sort of the critical value or the cutoff. If I get the chi-square more than 3.84 for that 2x2 table, I know it's going to be statistically significant. Now, I know all this sounds like gibberish. The good news, your program, Stata, will calculate the chi-square statistic for you. Sigh of relief. And it will not only calculate the statistic, but it will also turn it into a p-value for you. What Stata will not do is interpret it and explain it in English. You're going to have to do that yourself. In the next set of slides, we'll walk through an example of chi-square, and we'll see how we calculate it, how Stata calculates it, and then how we can present the findings in nice, simple, concise English.